Today we will be discussing about how can we estimate all the different parameters. Last time we have discussed how there is this CGD, which is the capacitance between the gate and the drain, CGS between the gate and the source, and also we have CDB between the drain and the bulk, and CSB, which is between the source and the bulk, and also there is a capacitance CGB between the gate and the bulk. So these are the different kinds of parasitic capacitance that exist in a MOS, and so these are different kinds of categorization of the different kinds of capacitance. Here we have seen that there is an overlap capacitance between this gate and this source, which is this C3. Due to this, because there's an overlap between these two regions, there is this small capacitance C3, and there is an overlap capacitance between this gate and the drain, the C4, and because there is a formation of the channel, so there will be a capacitance between the gate and the channel, which is the C1, right? C1 is the oxide capacitance between the gate and the channel, and moreover between the channel and the bulk, because this bulk is also a terminal, and there is also a kind of which is a depletion capacitance, like that. So these are the different kinds of capacitance that are there in a MOS. Now we'll try to see how do we estimate all these capacitance. So one important thing to be noted is these capacitance are dependent on the operating point of the device. So if the device is in linear region, the capacitance this will be different, and if the device is in saturation region, again these parasitics also will be different. So this parasitic capacitance vary based on the operating condition of the device. So in fact this capacitance, drain to bulk, this parasitic capacitance, it depends even on the drain voltage. So we will see how it depends. So now this gate and source drain region, if we see the 3D view, so this is the 3D view of this drain or source. So we'll see how this whole parasitic capacitance. So what happens, this C6 can be categorized into two types of parasitic capacitance. One is because we have this bottom layer, right? Bottom layer, which is bottom layer. This also is giving a capacitance between the basically this is a junction capacitance between this drain and the substrate, because we have this PN junction here, P and N, and we know whenever there is a PN junction, for a PN junction diode, there exists a depletion capacitance, like that. So, or junction capacitance we can say. So this is a kind of junction capacitance, and it can be divided into two categories. One is the bottom plate cap and the side wall capacitance. So we'll come in details of this one in the next after a few slides. So let's now focus on this C1. How do you find out this C1? Right, C1, which is responsible for CGS and CGD, like that. So or get to source and get to bulk. So whenever the MOS is in linear region, so we know that this channel is formed, right? We have this channel, so we have this these free electrons are there where the channel is formed. So this is in case of linear region. So of course the pinch off has not happened yet, so like that. Now what happens, the whole capacitance due to this plate and this plate, it gets divided into two parts, right? So we have this CGS, this CGS, and this CGD. So what happens, this whole capacitance, so we know that COX is the capacitance per unit area. So the whole capacitance, which is the whole capacitance, the total capacitance, which is COX WL, right? So we know that this is the leg L, or you can say this effective length L, and of course we have this W in this direction. So the whole total capacitance is COX WL, COX into WL. So this whole capacitance will be divided into CGS and CGD. So what basically we'll have here is half of this whole total capacitance, COX WL, and CGD will be half of COX WL, right? So this is the case when the transistor is in a linear region. So the pinch off has not formed, and the whole capacitance COX WL gets divided equally to half COX WL, and CGD is half COX WL. Now this is the case of the depletion capacitance. Now of course the overlap capacitance between the source and drain will always be there. So this will always be there, source and drain, gate and drain and gate and source, this overlap capacitance will be always there. So the total capacitance between this gate and the source will be the sum of this overlap capacitance and this capacitance, which is formed due to the channel. And similarly, the total capacitance between the gate and the drain will be summation of this overlap capacitance plus this capacitance. So I'll give a summary of this one in the next slide. So just I'm just explaining how this is. Now whenever a pinch off happens, so there is no this is basically the channel is not attached to drain anymore. So in this situation, this capacitance between the gate and the channel, the oxide capacitance between the gate and the channel. So in this situation, what will happen? This is in saturation region. So only there will be existing of gate and source capacitance, but of course it will not be COX WL. So in this situation, the capacitance that we'll have is CGS is 2/3 of COX WL, and CGD will be 0 because there is no connection or this is not connected anymore to this channel, like the gate. So that's why only there is a capacitance between the gate and the source. But of course the overlap capacitance will always be there. So now CGD will be only the overlap capacitance. There will be no channel and gate capacitance in saturation region. Now how this 2/3 ratio comes, right? This 2/3 ratio comes that I'm not going to do the derivation. You can refer to this book. So if you want to go in details, as such this is not much required in this course, but if you want to go in details, you can just refer, you can go to this book like that for the derivation. So I'm not going to cover in this course. So as I mentioned, so this overlap capacitance will always be there, but then we have this CZS will be 2/3 of COXWL and CZD will be 0. So now if I overall see the capacitance profile, so this is how it will be looking like that. So is this clear before I go to the next slide? Hello, is it clear?
Excuse me, sir.
Yes.
Excuse me, sir.
Yes.
Sir, if channel is not connected to the drain, there will be also a capacitance between drain and substance, because this is going to be reverse bias.
Oh yeah,
and highly reverse bias.
definitely. This I have not yet shown like that. So we'll come to this point later on. So here I am just focusing on the capacitance formed by the formed by the gate and the drain. So definitely that capacitance is there. So which I am going to come little later like that.
Okay.
Right. So this I am not covering here. It's always there like that. It's there. So what now currently what I'm focusing is most on the capacitance, which is basically the C1, right? So here in this slide we are just more focusing on C1. So how C1 varies with the operating point like that. Okay. So that reverse bias capacitance will definitely come. So how do we take care of it and how do we calculate it? That will come later on in the next slide. Okay. Yeah. So here is just
Yes, sir.
my
Okay.
focus was just how the a part of the CZS. I should not say this is a complete CZS. So a part of the CZS depends on this um, channel like that. So now if we see here, if we see this graph, it very nicely describes the whole capacitance due to the basically the between the this gate and the source, and gate and the drain. So what happens when the transistor is in off state? So there is no channel. So when the VGS is very low, less than VT8, so there is no channel form. There is no channel form. So my CGS and CGD will be only the overlap capacitance. Yeah. So only the overlap capacitance. So not that overlap capacitance is this is the capacitance. It's defined as per unit length, COV. That's why the total capacitance how it becomes is W into COV. So the overlap capacitance is this overlap capacitance. So or this overlap capacitance. So it is defined as capacitance per unit length. So length means in terms of this W like that. So if I multiply this W with COV, then I'll get this. I will get this overlap capacitance. So that's why whenever the transistor is in off state, so the CGS and CGD will only be the overlap capacitance. So because the channel has not formed, there will be no channel sorry a gate channel, that oxide capacitance will not be there. Now as we increase the VGS, whenever the transistor is in saturation region, because whenever like from cutoff it will go to saturation region, and considering that the VG is not high less than this VD, so it first starts with the saturation region. So what happens, as we have mentioned, the CGS it becomes 2/3 of WLCOX plus this COV will always be there. The overlap capacitance, this overlap capacitance will always be there. So now what will be is CGS will be this 2/3 COX WL plus the overlap capacitance. So that's how this is that's how we get this value to WL Cox plus W into COV, right? So now, but since the gate to drain is still 0, so only the overlap capacitance component will be here. So that's why you can see that in saturation region CZD is only the overlap capacitance part, W into COV, like that. So now as we go to the triad region, linear region, triad or linear region, then of course you see in both the cases it will be half Cox WL, half Cox WL. Both CGS and CZD will be half Cox WL plus the overlap capacitance. So you can see here plus the overlap capacitance and WL Cox half. So in the triad region, the whole capacitance will be this half Cox W by L, half Cox WL in plus the overlap capacitance, which is WCOV, and again CZD also will be half Cox WL plus this overlap capacitance. So this is how the complete MOS distribution, the distribution of the MOS capacitance, which is only just C, G, S, and C. CGD, right? So I should specifically mention here we are only focusing on CGS and CGD. So this is how the variation of the CGS and CGD. Is it clear? Hello?
Yes, sir.
Any questions on this? Okay. So now next is we will discuss the drain and the bulk and source and the bulk capacitance. So as I have mentioned, like so if we try to draw the 3D diagram of this one, 3D diagram, it will look something like this, right? So basically we have this like that, we have this cube kind of structure like that. So and then we have we have, I should say, so this area and this side wall area and the bottom layer, they are in reverse bias condition with the substrate, P substrate, right? So basically it's some kind of you can model it as a reverse bias diode, right? So now to make the simplification easy, what it is done is this bottom plate and this side wall plate, they are divided basically. So they are divided, right? So in the bottom plate there will be some capacitance, and in the side wall, because of this side wall, there will be a capacitance like that. So now that's why for this bottom plate there is this term called CJ, this CJ term, which means for the bottom plate right, CJ means the capacitance per unit area. So the capacitance per unit area is this is defined like that. Cj is a, that's why it's like farad per centimeter square. So this Cj is defined as the capacitance per unit area, and for the side wall it is defined as capacitance per unit length, like CjSW. Because this is defined as, because this height is almost fixed, right? So this height is not this height of the diffusion is almost fixed for a particular process. That's why we are defining, and the capacitance will be only depend on the perimeter. only perimeter. So the based on whatever the W that I choose, the parameter will be changing, right? Like that. So sorry, perimeter will be changing. So that's why this sidewall capacitance is defined as capacitance per unit length. So, but in this case, because because this W will mostly vary, W even X is also almost fixed, but there may be some variation. But the designer has an option for to vary the W, so that's why it is defined as capacitance per unit area, right? So this is the Cj is the capacitance per unit area, and for the side wall it is defined as Cj per unit per unit length. So the total capacitance, this one, the total depletion capacitance, C total will be summation of Cj. I need to multiply with the area, which is W into X, plus CJSW. So I need to multiply with the perimeter, so which is twice into length length plus breadth, because the height is like we are not considering the height, so only this perimeter, right? Perimeter of this rectangle. So that's why it is 2 into like that, length and breadth, length plus breadth. So is it clear? Is this explanation clear? Hello?
Sir,
Yes.
hello.
Any question? Yeah.
One minute.
Yes.
The sidewall capacitance, I mean, in the direction of width, is it the same in both sides? I mean, in the channel side and
yeah,
and the
yeah. This is same. That's why we are taking this common, right? So this is same, like approximately same, I should say. There may be little variation, but they are almost same, like that. Yeah. So I should mention one thing. So this we are just trying to make an approximation, right? So the actual capacitance may be little different, because it will definitely not be a perfect rectangle. There it will be something like that. It will be rounded, right? So here what we are trying to do is we are just trying to approximately estimate, right? So as a designer, we just need to approximately estimate. To get the exact value, we have to take the help of tool, right? So there are different kinds of device simulator which will give you the exact capacitance. But here as a designer, we are just trying to approximate what can be the value, like what will be the range, right? So because ultimately we have to go for the exact value, but for that we cannot do it, because we need to take the help of some mathematical solver. But here we are just trying to approximate it and try to get some estimate of the estimate of the all the capacitance. So as a designer, if we get an estimate, so we can just estimate what can be the performance, right? So depending upon this capacitance, I can tell, okay, what can be the bandwidth of the, in what range, right? In what range, although it may not be perfectly it may not be the perfect value, but at least we can range, okay, and this is the capacitance, and I can expect this much speed, or this much kind of power consumption, something like that. Agreed?
Okay, sir.
Yeah. So this is some kind of estimation. So as a designer, we should be able to estimate based on this theoretical like that. But the exact value, if you are using some kind of simulator and all, so all these things are already captured in that. So now, of course, now the other thing is, because this is an junction capacitance. As we know that the junction capacitance is again dependent on the because it is in a reverse bias condition. So we know that from the diode and from the device characteristics of the diode, this capacitance, this junction capacitance, depends even on the reverse bias voltage. So that's why a term of reverse bias voltage will come here. So this C depletion, the total depletion. So again, this is the this I have mentioned is an area, which is again is in Wx, and again this parameter is P, means perimeter is 2Wx, right? So and there is this term which also comes into picture that we need to incorporate it, which means that this Vr reverse bias voltage. Basically it's the voltage between, if we are considering it as drain, suppose for drain it will be VDB actually. So basically, because this for drain, so this is for drain bulk. So for the drain bulk capacitance, it will be, this is the VR. This VR is the potential difference between the drain and the bulk, right? So it is seen that this M and N are some constant. So and this M and N value are less than 1. So M and N are both less than 1.
Sir,
Yes.
sir, both quantities are not equal. How we can add them? One has a unit meter square, one has a unit meter.
Oh, yeah. One has a unit meter. I didn't get.
So your voice is not coming, sir, properly.
So hello, hello.
Yes, sir. Yes.
Are you able to hear? Yeah.
Yes, sir.
You see, this is, as I have mentioned earlier. This is capacitance per unit area, right? Per unit area, and this is the capacitance per unit length, right? This is what we have discussed here, right? That's the basic definition. Cj is the capacitance per unit area, and Czsw is the capacitance per unit length, right? So now if I multiply with the area, right, Wx is the area, so the whole this unit will be here only capacitance, right? Similarly, if I multiply with this perimeter, which is in length, maybe meter, so and this is since capacitance per unit length or per unit meter, that's why the whole this unit of this whole product will be an capacitance. Is it clear? So these are both capacitance and capacitance I am adding like that. So this is how these constants are defined. Basically, this is how these are some constants, or you can say technology dependent variable, right? So this area and parameter is on the device, on the designer side. So this value is given by the for particular process. So if I am designing in 180 nanometer process, then this value will be fixed for that process. This value, right? This value will be fixed in the sense that this is variable, but this value and this value will be fixed for a given process. So from a designer perspective, only I have access to this area and the perimeter. Is it clear?
Yes, sir.
Okay, great. Thank you for asking. At least I could clarify the thing. So these are all different kinds of capacitance, parasitic capacitance that exist in a that exist in that exist in a CMOS device. So just I think just to maybe sum up or going back. So we have discussed that there will be this depletion capacitance between the drain and the bulk, and also between the source and the bulk, and which we can do it, or which we can do it by drawing this 3D figure of the drain and the source, and then it can be divided into the bottom plate capacitance and the sidewall capacitance. Sidewall capacitance is defined as the capacitance per unit length, and depending upon the perimeter we can find out the capacitance, total capacitance due to the sidewall, and the bottom plate is defined as capacitance per unit area, and depending upon what is this area, I can find out the capacitance between the drain and the bulk, and the total capacitance will be added like that. And also this capacitance depends on the reverse bias voltage. So depending upon what's the reverse bias voltage, we can get the value like that. And similarly, this C1 which is between the gate and the channel is again depends upon the operating region. Depending upon whether it's a saturation region or in a triode or linear region, this capacitance will be divided into gate drain and gate source. And this overlap capacitance is always there, so which depends on the W, because this overlap is fixed, so that's why this is also defined as capacitance per unit length like that. So what I will do is I will try to give some problems on this, some maybe some assignment problems. So I think once you solve the assignment problems, things will be very clear like that. So okay, yeah, so at least you'll get some idea of the figures, what should be the what will are these values and all. So I'll try to give an assignment problem. So once you solve that assignment problem, I think things will be more clear and better. Okay. Sir? Yes.
Sir, can you explain the drain bulk capacitance or source bulk capacitance on the effect of on device operation?
I mean this drain bulk capacitance like that.
Yes, sir. How it is going to affect the characteristics of the device, switching speed, amplification?
Oh, definitely. Because you see, whenever let's go to a different. Okay, so yeah. So if I have this one, right? So I think this one we will as we in the future like lectures, as we discuss the different switching characteristics, so we will discuss more in detail, but here I'll just try to give a brief like that. So we know that this is a drain bulk capacitance, right? So we can model it as C dB, right? So this is directly coming in the drain node, which is basically this is carrying a signal. So because this capacitance is directly coming to the drain node, so this affects the switching speed. Like, so I think in the first lecture we have mentioned how the dynamic power dissipation is dependent on the capacitance at the drain node, right? For an inverter, so if I have an inverter here, so the again from PMOS also there will be a drain bulk capacitance, right? Some sort of from here also, right? In this case the bulk is of course the VDD, but it can be termed as AC ground. So these two capacitance, it affects the switching. Definitely it affects the dynamic power consumption, and also it affects the rise and fall time of the inverter like that. So if you are designing a digital circuit, or if you are going for the analog circuit, we say that the CDB depends very much. It affects the bandwidth of the device like that. Agree? Hello?
Sir, when these capacitance are going to come into existence, like high frequency or low frequency?
Yeah, mostly towards the high frequency, like especially when you are talking about very high speed operation, because then this comes into picture, because these are very small capacitance, but as we are going for this may be in terms of femtofarad like that, so these are very small capacitance. But when you are dealing with very high speed operation, even for the digital circuit, when you are going for a switching speed of suppose your clock speed is 1 gigahertz and all, then this pictures will this capacitance will come into play. But definitely when you are doing for when your clock speed is 1 megahertz or 1 kilohertz, it will not come into picture at all. But when we are discussing about like nowadays like the processor speeds and all are going for gigahertz of clock rate, right? Clocking rate are gigahertz range. So in gigahertz range, this all this capacitance come into picture like that. We cannot ignore anymore like that.
Okay, sir.
Okay.
Thank you.
Yeah. So I think as we further comes into the whenever we'll discuss the dynamic characteristics of the digital circuits, all these things will be coming back like that. So we will be taking account all this capacitance when we are discussing those part like that. Okay. Yeah. So
Yes.
yeah. So now next is of course now I think till now we have very briefly I have summarized different kind the MOS kind of all the MOS we have discussed about the linear region, saturation region, and then different kinds of capacitance. And now in the next 1 hour I will be discussing about the characteristics of inverter. So we'll go to the inverter design. And then we'll discuss the static characteristics of an inverter. But before that, I'll just like to give a brief overview of there's a different kind of technology which is known as Finfet technology, which is little different than the CMOS technology, but the operation is quite same. But only the look is little bit different. So as the process is going from like towards less than 20 nanometer, right? So as the process is less there or the gate length is going for 20 nanometer. You must have heard about 16 nanometer or 7 nanometer processors that is designed by Intel, or so you must have heard this. So currently the industries are using this 16 nanometer, 7 nanometer this process, mostly the 7 nanometer process. Many like all the chips are getting fabricated in a 7 nanometer process. So in that process is no more a normal, I should say, planar kind of design. So they have gone to a little bit change in the structure of how a CMOS looks. So that's this is called as Finfet technology. Finfet. It's a MOSFET only, but there is this term called Finfet has come into picture. So what basically is, so you can see that the gate, right? So this is the gate. Now this is the gate of this device, and this is the oxide, and this is the source, and this is the drain. So what basically is done is if we see this, let's go to some MOS figure here. So what it is done is, so what they have done is they have tried to rise this bar, right? Basically trying to go for some kind of this kind of this kind of, I should say, the going for I think it's difficult to draw here, but point here is they are trying to go for some kind of architecture where they are trying to pull out the channel, so that the gate has more control over the channel, right? So what is happening as the device size is becoming smaller and smaller, the gate is losing control over the channel, because there is like a lot of short channel effects which I have not discussed, but maybe we'll discuss towards the end of this course if time permits. But as the device size is becoming smaller and smaller, the gate is losing the control over the channel. So what they have done is, so they have tried to wrap around the gate over the channel. So you see, this is my source, this is the source, this is the source portion, this is the source, and this is the drain, like that. So the current is flowing in this direction, right? the channel is formed in this direction, and they have tried to wrap around the gate, right? So if you see here, the channel is formed beneath this, beneath this kind of rectangle. So we can say that the gate has more hold, right? Gate has more hold on the channel. So this is the oxide, this is the oxide of the channel, and this is the polysilicon, right? So the this gate has been wrapped around the, this channel. So because of which, what's happening is there is a lot of advantage. Even the leakage power, which we were discussing in the first class, the leakage power has reduced, because the gate has more control on the source and drain, like that. So of course, the in this, then how do you define the W? So what do you how do you define the W of the channel? So W of the channel is defined as right, the width of the channel. So this is basically the length of the channel, this is the length, and width of the channel is defined as the complete this 2 height will come here, 2 HF and plus this WF. So this is how the width of the channel that is defined, right? So this width of the channel is defined as WF plus 2 HF. So this is how in the new Finfet technology, because the main purpose is so that the gain has more hold on the channel to reduce the leakage and different effects like that. So this is how it looks basically. So this is my drain and the source, and there will be this gate, right? There will be gate, and because of this, there are other lot of things are there. So they go for some kind of discrete kind of, discrete kind of, because this is fixed, the W is fixed. So they try to go for multiple kinds of fins to get higher W. So we say that this is one fin, right? So and this W is fixed. W is fixed because what happens, this HF is fixed for a process, and even WF is fixed for a process, because we cannot, from a designer perspective, he cannot play around with even with this HF and even with the WF. So I should say that W is fixed, right? W is fixed. But then how do you go for multiple W? So if a designer wants to go for higher W, so what is done is they go for multiple fins like that. So they are called fins. They are called fin, right? That's why it's called the Finfet technology. So these are very small, maybe 100 nanometer. This whole W is 100 nanometer. So if I want to go for multiple higher width, then I have to go for multiple pins. So compared to the planar technology, we can the W of the transistor has become discretized, right? We cannot take any value of the W width like that. So that's why in this Finfet technology, but of course the resolution of that fin size is very small, 100 nanometer. So that's why it's possible like so that kind of resolution is fine, like even for analog design or digital design. So that's why, like although it's discrete, it's still fine like that. So this is how it looks. So this is how, like, multiple, these are two fins, and this is the gate. So this is a fins like that. So so this is how the new Finfet technology. So I just want to just give a brief overview. I don't want to go too much in detail, just so that you become aware of the what is the Finfet technology. Of course, again, if time permits, again we may come back at the end of this course, and we can also discuss why exactly we are going for this kind of technology. So the main motivation is, as I mentioned, to reduce the leakage current, and so that the gate has more control over the this channel, right? Because these with the decrease of the length, or with the decrease of the length, the gate is losing control over the channel. So this is very in layman terms I am just explaining, but of course we can discuss from the device perspective also. But again, as I mentioned, if time permits, at the end maybe we can discuss a little bit about this Finfet technology more from device perspective, like how it is helping the like reducing the leakage and other stuff like that. Is it clear? Any doubt on this? Hello? Hello?
No, sir.
Okay. Yes.
Hello.
Yes.
So can you tell about this WF and HF once again? Like, what is this W?
What is this W? Okay, so this you see this, if you see here this gate and this oxide, you are able to understand this, right? So it is wrapped around this channel, right? Source and drain channel. So this WF is this I should say this is width I should say width of this rectangle, right? And HF is the height, right? So because my channel is formed all across this one here, right? All across this one. That's why my effective width of the transistor will be this one, because you see the gate is all around this I should say this substrate. You should say this substrate. So so this is, that's why it is H is coming twice, right? HF is coming twice and WF is coming once. So that's why it's total effective W is WF plus twice HF. Is it clear now?
So basically, like, this gate has a control over the perimeter of like WF
Yes,
plus 2H.
yes. Not exactly perimeter, because this is left. So if not the total whole rectangle, but at least this 2H and 2F. Yeah, you are correct like that. So they are trying to go for, trying to wrap around all those this rectangle like that. Yes. Hello.
Whereas MOSFET have only WF.
Yeah, we have only WF. You are exactly right. Yeah, we are only WF. Yeah. So
Okay.
because of this, they are going to they are able to implement the transistor in a very small area like that. Getting right? The main reason is going for a smaller technology, as I mentioned, right? Going for very like less than 20 nanometer. So they are trying to go for very small kind of. So that's why they are going to wrap around the channel across wrap around the gate across this channel. Yeah. Clear, right? Yeah. Hello?
Yes.
Okay,
Yes,
okay,
sir.
okay. So this is the Finfet technology. So yeah, in fact, people are even trying for trying to make some trying to wrap around totally across the channel. So we have the complete parameter, something like this, right? We have this channel here, and we have the so something like I have a channel here, right? I have this my oxide is here. My gate is here, right? So this is my gate, this is my oxide, right? This is my channel, right? So that the this gate has a complete control on the like that. But of course this is just under research. There is no product. This is there is a product for this. As I mentioned, all the 7 nanometer processors are using this one, this Finfet technology. This is just a concept. It's still in research, because the manufacturing is an issue here. Like, although it is possible, but the how do we do this structure? It's not still it's under research. So as people are trying to go for very small, like less than 5 nanometer, people are thinking about this kind of structure. But of course, this is not yet in the product level. This is just in the research like that. But this has they started like in the production. So all the new processors with Finfet technology uses this one. Okay. So yeah, so this is at the end of the discussion of the this one MOSFETs. So now next we will discuss the circuits like that. Okay.